All right, this is lecture 20, so let's continue our discussion of superposition and standing waves. So last time we started talking about the principle of superposition. It was basically if you have different waves or different pulses in a medium, in the regime where the waves are described by linear equations, which is the regime we're interested in this course, we have the superposition principle. So this principle simply says that d of x and t is, let's say, sum over j dj of x and t, where dj's are the waves from multiple sources. And a particular example we looked at was two sinusoidal waves, one traveling to the right and another with the same wavelength, same amplitude, traveling to the left. So something like this can be described by a sine kx plus omega t, and something like this can be described by a sine kx minus omega t. So let's say that's d1 x and t, and that's d2 x and t. Then the wave pattern that emerges, d of x and t, which is a superposition, it's just simply adding these displacements, is given by 2a sine kx cosine omega t. So this sine kx is a position-dependent amplitude. And then what happens is, we see a product of a function of position, which gives us, say that's the function of position. And then it multiplies this cosine that goes between 0 and 1. So it gives rise to oscillations between these minima and maxima. So at every point, we're going to get these oscillations, and the wave seems to be just standing there. There's no concept of it traveling. And if you break it up into these traveling components, they're traveling, you have one component going to the left, one component going to the right with the same speed. All right. So then one can ask, okay, so how can we create these different waves? Well, one is, you can really create vibrations at 2 points of a wire. But there's an easier way, and that's using the reflection of pulses. So we talked a little bit about what happens when you have an interface between two different media for the propagation of waves. So for example, if you have, let's say, a light string and a heavier or thicker string, something like that, and if you have a pulse here traveling toward this interface, well, what happens is it gets reflected and it gets also inverted. So something like this happens. And also some part of it will enter the next medium in general, and so it will be something like this. It will be moving slower in the thicker medium, so it will be kind of closer to the interface, right? So let's say this reflection has traveled this much. Here it has traveled less. It's going to be somewhere over here. And they will both have a smaller amplitude than the incident pulse because of energy conservation, basically. So something like this happens. Now, it gets inverted. Interestingly, if you have the opposite scenario, so if you have a wave incident from the thick medium where the speed is smaller. So if you have something like this, incident on that interface, it gets reflected, but it doesn't get inverted. So it will look something like that when it's reflected. It comes back this way, and you're going to get some part of it going the other way into the lighter medium. Okay, so an extreme case of this is if you have a thick wall, right? It gives you something known as a fixed end boundary condition. So if that wall is really heavy, it cannot support propagation of waves, and basically this point is pinned to the wall, so the wall isn't moving. This point is pinned, so at that point, so let's say that's X end or whatever that is. That's the position at where the string is connected to the wall. For all times, that's equal to 0, right? It's pinned at that point. Okay. So now suppose we send a pulse in, and it gets reflected after some time. So it comes back like that. An inverted version of it comes down. It's helpful to think a little bit about what happens, right, in the intermediate times where not all of the pulses reached kind of the endpoint, right? So basically, suppose, half of the pulses reached the endpoint. So let me just draw a more maybe elaborate pulse, right? So imagine something like this, just to visualize it. Maybe let's say it's a triangular pulse like that. And it's moving this way. Okay. So it has just reached the interface, right? If there were no wall there, right? So without a wall, it would just keep going, right? Something like this would happen. But now this part of it, right, must be reflected because it cannot enter the wall. And when it gets reflected, how does it get reflected? Well, it also gets inverted. So if you think about what would have happened, well, this part that hasn't reached the wall is there. This part that has already bounced back from the wall, if you wish, must get inverted like this, right? So here, this point is just barely touching the wall. And these are the points these are the parts of the pulse that hit the wall a while back. So now they're reflected and have moved back. So that's why they're kind of over here. And everything is reflected. If it was a positive displacement, there's a negative displacement corresponding to that. So if you want to construct this wave a little bit later, now you have the superposition of the incident part and the reflected part inside the string. So let's draw this. So up to here, I just have my incident pulse that looks like this. And then over here, well, it just goes to 0 here, right? Because that's the negative of, these have the same heights here, right? So when it's inverted, this length is equal to that, and it kills the displacement. And that's good because it enforces the boundary condition that the displacement at the point of contact is 0, as we expect. So it looks something like this at that intermediate time. right? And then, you know, as more time goes on, you know, all of it gets reflected. So eventually, maybe at some longer time, all this pulse is reflected from the wall. So once the whole thing is reflected, so later, let's say when, again, the wall is here, if there was no wall, the whole thing had gone through. So now the whole thing is reflected. It looks like this now. Okay, so basically the way to construct this is to, the easiest way, at least one easy way, is to think about, forget about the barrier, forget about the reflecting wall, and imagine what the pulse would be like here. So some part of it will be on the other side, and then just reflect the part that will be on the other, or would be on the other side if there was no wall, and then look at the superposition with whatever incident wave you have on the left hand side. All right, so we talked a little bit about the details of the intermediate times, but ultimately, you know, this one gets reflected, right? So now, if you have a sinusoidal wave incident on your wall, it gets reflected, but there's also the part that's incident, right? So suppose, you know, you have a wall here, and you just keep generating this sine wave. So maybe if there was no wall, it would just go through like that, right? And let's say, imagine a very long string. So this is moving this way. Okay, so if I want to think about what my, let's say that's a 0 here. So this is slightly above 0, for example. Okay, so what would the wave pattern look like? Well, it's gonna be 2 sine waves, right? Because the reflection is just taking this and reflecting it. So let's say this is my wall here, and looking into this region like that. Here, you know, you have this. So I need to take that and reflect it. So this height comes, it becomes a negative of that. And then it gets reflected like this. So, and now the incident one is going this way, the reflected one is going that way. So we end up with some phase shift. It's not going to be exactly this particular form unless we put the origin at some convenient place. But it's going to be 2 waves with the same amplitude and the same wavelength traveling in the opposite direction. So potentially you can just drive a string with some frequency, inject some sinusoidal wave into it, and then you put some boundary at the other end, and then it gets reflected, and then the incident wave interferes with the reflected wave, and that can give rise to a standing wave. Now, it turns out if you find a stable standing wave, you cannot have just any wavelength or any frequency, right? So that's a consequence of the boundary condition. So consider fixed boundary condition. So on both sides, let's say we have some fixed walls. So kind of like a guitar string that's maybe pinned at 2 ends. So then let's call that 0, let's call that L, right? So we have a string of length L with fixed boundary conditions, which means d of 0 and t is equal to d of L and t at those 2 points here and here. For all times the displacement is 0. And then we form some standing wave pattern. So this standing wave pattern must have nodes, right? At those 2 points. Those are 2 points where there is no displacement, so those are the nodes. And the distance between 2 nodes is always lambda over 2, right? If you think about a general standing wave pattern. So if those are nodes, if here and here I have nodes, I must fit an integer number of lambda over 2's, right, inside the entire string. So maybe I can do this. Well, I can fit 1 lambda over 2. Something like that. Let me draw it a bit more symmetrically. Or I can fit 2 of them. So that adds 1 more node. Okay. You can think about the full pattern of the standing wave. Or I can fit 3. So 1, 2, 3. Okay, so in this case, L is just lambda over 2. In this case, L is 2 times lambda over 2. In this case, L is 3 times lambda over 2. So this number labels the allowed wavelength, right? So in general, we can say L is m times lambda m over 2. Lambda m is allowed wavelength for standing wave with fixed boundary condition. Okay, so this is also the number of antinodes, right? So you have 1 antinode, here you have 2, here you have 3. All right, so then we can solve, like given m, we can solve for these allowed lambdas. So lambda m now becomes 2 times L over m. And then we can solve for the allowed frequency. So lambda m times fm is v. The speed of propagation is independent of the mode, of the frequency, etc. So what we find is fm is v over lambda m, which is mv over 2l. So it turns out if you have a string, right, that's pinned at both ends, and you want to generate some standing wave pattern, and you want to drive one point of it, and then you have these reflections, you know, kind of bouncing off and interfering and giving rise to that interference pattern corresponding to the standing wave, you need to have the right frequency. It must be an integer multiple of v over 2l, where m is 1, 2, 3, etc. So f1, which is the smallest possible frequency, is known as the fundamental frequency. Okay. Now, so this integer m, which is also the number of antinodes, which is the number of half wavelengths you can fit into your entire string, is known as the mode number. M is called the mode number. Okay, so let's take a look at this example here. It's a very simple example. Yeah, take a few seconds, pause the video, try to figure out the answer. All right, so we just count the number of antinodes, or the number of half wavelengths. So 1, 2, 3, 4, 5. And that's our answer, right? That's the mode number. The number of antinodes is the mode number. Okay, what about this? So again, try to figure out the answer and come back when you're ready. All right, so we have a standing wave on a string. It vibrates as shown, right? Like that. So that's mode number 2, right? You have 2 half wavelength fitting here. You have 2 antinodes. Now, suppose the string tension is reduced to 1/4 its original value, while the frequency and length are kept unchanged. Which standing wave pattern is produced? So tension. Remember, the speed is the square root of tension over the linear mass density. So if you reduce the tension to 1/4 of its original value, then the speed becomes half, right? The square root of 1/4 is 1/2. Becomes 1/2 its original value. So lambda times f is v. Okay. So we're not changing the frequency, right? The frequency is kept unchanged. So if v goes down by a factor of 2, lambda must go down by a factor of 2. So previously we fit 2 half lambdas. Now we should fit 4 half lambdas, right? Because lambda is just half of its initial value. So C is the correct answer. Yeah, so that's another way to argue this. So V is cut or reduced by 1/2. So then M must be doubled to keep the frequency the same from this formula. Okay. And so this example we did for transverse waves on a string that's under tension, but mirrors basically for electromagnetic wave or light, which is a special case of electromagnetic wave, just a given frequency range. Can act like can give rise to fixed boundary conditions. Basically, they force the electric field to become 0 here at the interface, because if it's fully reflecting, then nothing goes through, so there can't be, because of continuity, there's no field on the other side, so the field must be 0 at the boundary. Now we can apply all of what we did to the case of light, and we're gonna get very large m's, because typical wavelength are tiny, or order of nanometers or hundreds of nanometers, and length of a typical laser cavity, for example, is order centimeters. But it's essentially the same physics. So we talked about fixed boundary conditions, right, where the thing that's oscillating, in this case the displacement, is 0 at the boundary. We also have something called the free boundary condition, where the string is not at all restricted, for example, or you can construct it for the case of a string if you maybe put like a rod here, and there is a frictionless loop around it that can freely move up and down. And then you have this wave that's incident. So that point is moving up and down freely. Yeah, so let's say how we can argue this. So imagine this is massless, or the ring has really tiny mass, massless, frictionless. Very idealized case, but then where the string is attached to it, it cannot have a vertical component because there's no friction, there's no mass. So there cannot be any net vertical force on the string because its mass is 0. So Fy, sum over Fy is m ring, the mass of the ring, times the acceleration of ring. And if mass goes to 0, then this side is 0. So sum of the forces in the vertical direction must be 0. So the tension over here can only be horizontal, and then it can cancel out with some normal force from the rod, right? So there cannot be any vertical component because there is no friction, and only friction can cause another vertical force that would cancel it out. So the boundary condition we get here is that the rope is horizontal at that point. So that means that if you take the derivative with respect to x of this quantity for any time, you fix time, right? If you fix time, it's like looking at some snapshot figure like here. And then at that point, at x equal here, whatever that is, let's call it x boundary, I guess, or x end. So at that point, this must be 0. So instead of the quantity itself, the displacement itself being 0, its derivative with respect to the position is 0. And now if you think about the pattern that emerges, the standing wave pattern that emerges from reflection from this rod, well, that pattern must also satisfy this condition, right? So therefore it means that at that point we have an antinode. Okay. So now we can think about various boundary conditions. So we can have fixed, which we already discussed. We can have fixed free, we can have free, and we can have free fixed. So free fixed and fixed free are basically the same, but so let's think about, for example, fixed free boundary condition, right? Fixed free boundary condition. So yeah, BC stands for boundary conditions. Also for British Columbia, but not here. Okay, so let's say here I have a fixed wall. Here I have one of these boundary conditions I've engineered where I'm going to get an antinode. So this is fixed, this is free. Okay, so here I have a node. Here I have an antinode. So if you again think about the general pattern of these standing waves, well, the distance between nodes is lambda over 2, and the distance between a node and an antinode is lambda over 4, right? So how can we how can we get a situation where on one end, let's say on the left here, we have a node, on the other side we have an antinode, right? So if you think about it this way, there's no point in memorizing these. There are lots of formulas, right, for various boundary conditions that one can memorize. But if you remember the argument of why it's happening, it's really easy to just visualize this pattern and figure out what the formula is. So yeah, so if I start from one node, right, the first antinode that I hit is over here, so that's at lambda over 4. And then the next one, well, I have to add lambda over 2 to my lambda over 4. So in general, let's say, again, fixed free, I'm going to get something like this, where L is lambda over 4, right? That's the lowest frequency mode. Then you have one of these lambda over 4s, right? You get a node, and then you must have one full lambda over 2. So lambda over 4, lambda over 2. And in general, you're going to get one lambda over 4 plus an integer number, which can also be 0, right, of lambda over 2s. Okay, so in this case, we found L is lambda over 4. In this case, becomes lambda over 2 plus lambda over 4, which is 3 lambda over 4. Again, the next one, I have 2 of these lambda over 2s, 1, 2, and 1 lambda over 4. So now it's going to be 5 lambda over 4s, right? This is lambda over 4, then this is another 2 of them, another 2 of them, so it's going to be 5 lambda over 4. And you see the general pattern. So L is going to be now M times lambda over 4, where M, instead of being any integer, is an odd integer. 1, 3, 5, 7, etc. So that's the pattern we get. Let's call this lambda M, right? It depends on this mode number. And again, the frequency, we know that lambda M times Fm is V. So Fm is V over lambda M. So becomes, let's write lambda M here, is 4L over M, right? So that's MV over 4L. Again, M is 1, 3, 5, etc. All right. So that was the case of fixed free. And you see that free fixed is the same, right? It really doesn't matter if, you just take the mirror image. So if this side is free and the other side is fixed, we just find the mirror image of these. And then we have the same allowed wavelengths and allowed frequencies. Let's also take a look at free. Okay, so free again, thinking about the general pattern of standing waves. Well, we want to have antinodes at the end. So let's say this is one end. Then we can either have the next one here or here or here. But these are shifted by a distance lambda over 2, right? So we find the same condition as the fix. We have to fit an integer number of lambda over 2s. Same as fixed. In the sense that L is M lambda M over 2. And then it gives, lambda M in terms of L and M. It gives the frequencies in terms of L and M, etc. All right, let's practice a little bit. So I want to work out one example. All right, here's an example. So a snapshot graph is given at t equal 0. We have a pulse, a triangle between, let's say, 1 centimeter and 3 centimeters. Goes up to a height of, or a displacement of 2 centimeters at x equal 2. This whole thing is moving to the left, or to the right rather, toward this fixed wall. There's also another pulse here, goes to -1 between 5 and 6 centimeters. So that's a snapshot at t equals 0. Both of them are moving this way to the right. And the problem is asking us to draw snapshot graphs at several times and stack them vertically at t equal 2, 4, 6, and 8 seconds. Okay? So, yeah, so let's do that. So let me just try to stack them vertically below the same thing. Here, this is my fixed wall. All right, so at t equal, let's say that's the x-axis again. We draw it here. 1, 2, 3, 4, 5, 6. Yeah, didn't work. So say this is here I have 4. Here I have 6, here I have 2. Okay, so at t equal 2 seconds, right, we're moving with speed 1 meters per second. So the pulses should move forward by 1 centimeter per second. Sorry. The distances are in centimeters. That's 1 centimeter per second. So after 2 seconds, so let's say t equal 2, this should be between 3 and 5, right? With a peak at 4 here. The height is again 2. This should be between 7 and 8. So this one is just hitting the wall. Yeah, so I shift them forward by 2 centimeters, right? They're moving at speed 1 centimeter per second, 2 seconds has passed. So that was easy. Now the next one, say 4, 6, 2. Okay, so now if another 2 seconds has passed from this, so I need to shift them forward again by 2 centimeters, right? So this one that's now between 3 and 5 will be between 5 and 7. Now this one, where would it be? Well, if the wall were not there, right, it would shift forward by a distance of 2 centimeters. So this end will be here, 1 centimeter away, right? So it started here. So it looked like that. Now, but it got reflected, right? And in that reflection, it gets inverted as well. So now you construct a mirror image and invert it. So it's now one, this end is 1 meter or 1 centimeter away from the wall. This is 2 centimeters away from the wall. So this one that's here must come here, right, after getting reflected. And this one, which is now a longer distance, reflected earlier, so it's now 2 centimeters this way, and it's reflected like that. So our wave is going to be a superposition of these two pulses. Okay, so then how do I draw this? So that's t equal 4. So using this construction, this is 4, this is 5 here. So between 5 and 6, I just have this pulse. It goes up from 5 to 6, and it reaches a height of, let's say, 2 centimeters, that maximum. Then between 6 and 6.5, let's say it's, so suppose 7 is here, 6.5 is here. It reaches a height, you have 1 from here, and you also have 1 from here, right? So you're adding a line to a line, you should be getting a line. And it seems the displacement remains constant, so it must be something like this, horizontal line, right? Because from here to here I have 2, halfway between I'm going to get a displacement of, so a 1, right? So if this is half of that, these are similar triangles, this is going to be half of that, which is 1, and then it gets added to another 1, so it's going to be this. And then at 7 now, so this is 6.5, at 7 it goes back again to 0. Again, here in this region I'm adding a line to a line, so I'm going to get another line. So that's the sum of these at 4. And yeah, we can keep going, just keep drawing these. So let's say at t equals 6 now, another 2 seconds has passed. So now we go back to this figure, right, the one without reflection, and then be reflected. So let's think about t equals 6. So now here, this one, if there was no wall, now it's between 9 and 10. So it should be now between 11 and 12. So 11. And this one, where is this one? Again, two more seconds. It gets shifted forward by 2 centimeters. So 7 goes to 9. And 5 goes to 7. So if there were no wall there to reflect these, it would look like that. But there is a wall, so what happens? Well, you have this is on this side. This one now gets reflected, right? And inverted. So here you have a height of 2, you go to -2 and look like that. This is the reflection of this part. This gets reflected and inverted, so 8 to 11 is 3, so we have to come back by 3, 7, 6, 5, right? So it's going to be now between 5 and 4, and it's upward. It looks like that. Now, if you do the superposition, this and this cancel out. They're in the same region. They have at every point one is negative the other one. So we're just going to see this little bump between 4 centimeters and 5 centimeters, and the rest cancels out. T equal 6 seconds. So this already, is moving this way, right? It's a reflection. So we can forget about reflecting this now. We know what's happening. So if I again, keep going. So if I go to 8 seconds, well, now this one, now it's between 4 and 5. So coming back by 2 centimeters, it's going to be between 2 and 3. Right? And this one here is between 7 and 8, right? So let's say here is 6, here is 7. So it's now like that. If it moves forward by another 2 centimeters, it's going to be between 9 and 11, and then it gets reflected around the wall, which is 8. So it's 1 centimeter on this side, so it's going to come back between 7 and 5, right? So 9 goes to 7, 11 goes to 5. Yeah, so now the whole thing is reflected. So when they are near the wall, they interfere. So you have this upward pulse, this downward smaller pulse getting close to the wall. They reach the wall. Then for this one at 4 seconds, this one is not reflected. This is reflected, and then the reflection gives you this superposition. At t equals 6 seconds, this is fully reflected, so it's moving away, and it no longer interferes with this one. This, part of it, the bigger triangle, part of it gets reflected and actually completely cancels out the incident part. And then a little bit later, also the incident part gets reflected, so you have the incident one, just the whole thing inverted and reflected coming back. Okay, so this was a good problem, just drawing these things and practicing both what happens when you get reflected from a medium that has a slower kind of speed, in this case 0 speed of propagation, so you have this inversion without changing the amplitude. We have full inversion and reflection, and also just practicing with the superposition principle, right? Adding these different pulses together. All right, so that's a good place to stop here. In the next lecture, we'll get more practice about these boundary conditions for standing waves, and we also talk about them in terms of, or in the context of sound waves. So there we have 2 different pictures. There's a pressure picture and the displacement picture, and they're complementary. So we'll discuss what different boundary conditions mean and how we can extract the frequencies of standing waves.